ఇంకా 29 మెంబర్స్ ఉన్నారు. సో చూద్దాం సార్, నాకు తెలిసి జాయిన్ అవుతారేమో. ఇంకా ఒక 100 మెంబర్స్ అయితే మనం స్టార్ట్ చేసేద్దాం. ఓకేనా? హలో,
ఇప్పుడు మన వాయిస్ వినిపించింది కదా ఇక్కడ?
లేదు సార్, వేరే వీడియో ప్లే చేయాలి.
Good morning. Good morning to all the faculty members over here, respected directors of Sri Venkateswara Group of Colleges in absence, I. Kishore Garu, Director ISVC, and Visakha Garu, Principal SVCT, and all the faculty members joined in this FDP program. Welcome to you all to this presentation of this 4-day FDP on advanced technologies in chemical science research. Myself, Dr. Prasanna Kumar, Associate Professor of Chemistry and HOD of Biosynthesis Department, SVCT. Actually, due to this COVID-19 pandemic situation, we are all restricted to offline academic activities, of course, domestic activities also. So in this regard, SVCT started webinar series since the first week of April. Since then, we are conducting so many webinars, FDPs, and workshops, etc., etc. So today, I am very happy to announce that approximately 400 participants are registered in this FDP program. Now, I would like to invite Dr. V. Surendra Reddy Garu, Principal, Sri Venkateswara College of Engineering and Technology, to say a few words regarding this session. So, Principal, sir.
Yeah.
Sir.
First of all, good morning, all of you. And today is the World Population Day. So during this occasion, fortunately, we are also conducting this FDP during this Population Day. And this is not the first time. So every department is trying to do their efforts for sharing their knowledge towards to faculty fraternity as well as student community. So I would like to thank all the participants for your encouragement and for your huge response. And today our research person, Dr. S. Paul Douglas Garu, I would like to thank you for accepting our invitation and for delivering your great lecture during this occasion. And all the best for the science and BSH department. So thank you, Vananda.
So thank you, sir. Now, I request Hi Kishore Garu, Director, ISVC, to deliver his message regarding this session. Sir, Kishore Garu.
A very good morning to all the participants and to all the organizers. Firstly, I congratulate the BSNHN team of our institution for starting the workshop on FDP program on advanced technologies in chemical science and research. I'm very happy that we have started this workshop. Firstly, I would like to thank Dr. S. Paul Douglas Garu for accepting the request and spending some time to share his expertise and knowledge with all the faculty and the participants. I'm pretty sure that it will be a quite useful session to all the participants, and these 4 days are going to be very knowledge gaining and very useful for all the participants. So I wish all the participants to make sure that they try to get the best out of the online workshop, and thank you all.
So thank you, sir. Thank you so much, sir. Thank you so much, sir. Now, I am very happy to introduce today's speaker. He is a guru to so many students, scholars, and faculty members like me. He is Dr. S. Paul Douglas Garu, HOD, Department of Engineering Chemistry, Engg.College of Engineering, Andhra University. Now, I request Mr. A. Appalnaid Garu, Assistant Professor of Chemistry, to introduce today's speaker.
Yes, sir. Good morning, one and all. Okay, sir. Thank you, sir. Good morning, one and all. Distinguished dignitary, stalwart of chemistry, HOD, Department of Engineering Chemistry, Engg.College of Engineering, Andhra University. We are glad to invite you, sir, again, sir, to this inauguration of 4-day FDP in advanced technologies, chemical sciences and research. Myself, Appalnaid Arnapalli, Assistant Professor. I am very proud to share few words about his achievement and honors. He has spanned of 29 years of teaching experience, 15 years in teacher education, 14 years in organic chemistry. He guided 10 MPhil degree scholars and 10 MTech projects. 29 scholars were successfully completed and awarded PhD under his able guidance. More than 80 national and international journals and research publications for a feather of his crown. He attended more than 50 classes and workshops. Jan number of citations 172, H index 8, and 1 to indexes are 6. And also he visited South Africa and Israel. Sir, it is very too honor to me, sir, to invite you to this FDP, sir. Thank you once again. Thank you, sir.
Sir?
Yeah.
Paul Douglas, sir. Sir, I hand over this session to you, sir. Paul Douglas,
thank you.
Please.
Yeah, thank you so much, all the organizers, especially the director of the college, the principal of the college, for their good words in introducing me. And I thank head of the department, Prasanna Kumar garu, and all the faculty members for this today's webinar for advances in chemical sciences. I know this lecture will be quite interesting for all the people who are going to take up research in the area of nanotechnology. Last time I was sharing the work which I have done, maybe one scholar's work or 2-3 scholars' work, but this time I thought I could really teach you something so that those who want to do research in nanotechnology area, it will be of a maybe like a basic guideline for you. So that's why I thought I could share this to you. Especially I thank the organizers for giving me this opportunity. I just want to share my screen. Would you able to see my screen? Hello?
No, sir, not yet, sir.
1 second. Share.
No, sir.
And okay, screen. Could you able to see now?
Yes, sir. Yes, sir.
Okay, screen. Could you see?
Yes, sir.
Yes, sir, yes, sir. We were able
Yes, sir.
to see the screen.
Yeah. Thank you so much. So this topic which I have taken for this morning session is biosynthesis of nanoparticles. This will, I just want to take you through a long journey. I hope I can complete that in time. I think I have some 45 minutes to 1 hour to go, I think. Hope many of the things which you need to know about this area called as biosynthesis of nanoparticles, how you can use bio methods or biogenetic methods for this area. For that purpose I have taken, but along with that I want to tell you why we need to do this, why we need to go, what are the advantages of doing it, why if I really want to do research in this area, what I need to know, what I need to understand from these particular things will be the main criteria in this one. So for maybe if you are really entering into this area of nanotechnology and nanoparticles, this is where you really see nanoparticles or the nanotechnology in this area. When I look to the size of it, if you know the size of a football will be in 22 centimeters. If I see a small flea, it will be 1 millimeter. Our red blood cells are 7 micrometers in size. Then if you see our human hair, its diameter is around 80 micrometers. But if you come down and virus size is around 150 nanometers. If you see the titanium dioxide used in sunscreen lotions, it will be in the size of 35 nanometers. If you see a buckyball, it is 0.8 nanometers. And if you see the thickness of a strand of DNA, it will be 2 nanometers. So we actually, if you go one more step down, we get into atomic level, and that's where we actually stop there. So we have a quite range from 1 meter to 1 to the power of 10 of a meter in this particular scale. But we are interested in the context of 100 nanometers to 1 nanometer. That is 10 to the power of -7 of a meter to 10 to the power of -9 of a meter. If any object of one of its dimension is in the range of in between 1 to 100 nanometers, maybe any of the X, Y, or Z axis, then we are calling those particles as nanoparticles. We have a similar image there, just to give a clarification we have neurons. They are around 200 micrometers in size. Then you have a similar scale that is given. I just took these images from Google so that they are giving us some understanding. If you take a pollen of a flower, it comes around 100 micrometers. If you take bacteria, it comes around 1 micrometer. Then if you before by Norio Taniguchi. So it's maybe roughly around 30-35 years. That word nanotechnology has come. Now it is more than 75 years that the idea of nanoparticles have come, but it is there right from the beginning. Maybe it is there along with our universe, it is there along with our fog, along with our earth, it is there in our system, it is there everywhere. Maybe only at late we could able to see its importance, we could able to see the potential in this particular area, and now it has emerged as one of the very, very strong technological areas in all science and technology. So this is it is nanotechnology. It is art, and both art and science of manipulating the matter at the nanoscale. So we know about bulk material, we know about material at a larger dimension, but we are trying to now manipulate the matter at the nanoscale, and we want to do it with clear precision. We want to do it in simple methods, and at the same time we want to do at low cost. We have certain instruments which are very, very costly on one side. Their maintenance is costly. They are very costly in terms of their acquisition and also their maintenance. On the other side, we have so simple methods that we could able to do even in our kitchen, even in our ordinary laboratories, even in our teacup. That's what we are going to see by the end of it. So these particular particles are invisible to our naked eye, and there the question starts. If we can't see them, how we can prepare them? If we can't see them, how we can carry them? If we can't see them, how we can actually collect them and then keep them with us so that we can use them? So even though for naked eye this size is invisible, maybe the actual size, but we have a mechanism to prepare them, to pull them up, to separate them, and then we can use them for our various purposes. So we have, maybe I'll be going directly into these particular things regarding the preparation of these particular material, because I'm more interested to slowly take you toward the biosynthetic methods or biogenic methods. So that's why I just want you to run through up to 2 more stages prior to biogenic synthesis. That is both physical methods and also the chemical methods that are required there. So we have 2 approaches that are available throughout the literature. We call them as bottom up, and the other one is called as top down. If you see in the image on the screen on the right side, if you have a bulk, maybe in centimeter size or in more than centimeter or any of the size, if you start breaking it, and if you start breaking it, and then if you can make it into smaller pieces, you still go for further powdering, you use higher energy, you do something in such a way that you make a fine powder till it comes to the size of nano size. So if you are coming from top to bottom, if you are breaking the molecule, breaking the substance from a bulk size in which you can handle it maybe in 4 centimeter by 4 centimeter cube, and then you start breaking it, make 1 centimeter, then come up to 1 millimeter, then still break them, so that you get your nanoparticles between 1 to 100 nanometers. If you are coming from that direction, from the other hand, we have something called as, if you have these particles at the atomic level and you can make them, you can design them so that you can bring them into clusters and then make them increase their size by clubbing them together. This approach we are calling them as the bottom up approach. So one is from top, I am coming down. So that's why I'm calling this this is called as top down approach. And the other one on the right side, from the bottom one, if I am taking from the atom level, or if I have ions, I can convert them into atoms first, and then I can build them up so that my required size, or the size which I am looking forward, those particles I can make. So these two approaches are either, so in bottom-up approach, we are assembling the atoms and molecules together, and we are constructing the structures in such a way that our required dimension, our required composition is prepared. On the other hand, in top-down approach, we want to break down. So if you see somebody using a very high energy hammers in such a way that they make a fine powder of granite, and then if they can make still further, use some mesh and then make like a fine powder. Maybe that's how they go up to certain level even in many of the metallurgical processes to get fine powder up to micro size. Then only they require specialized devices to go up to the nano size. So that's why these two approaches will be helpful. We'll be seeing them how they are doing this. So in top-down approach, that's why we see that it is used by externally controlled devices, and then in top-down approach we go for microfabrication methods. We need to use some externally controlled tools. We need to cut them, we need to break them, make a fine powder, we need to mill them, and then we need to get the desired shape. So we use this particular word called as ball milling process, or high energy ball milling process. If you have little time, just simply Google that word either in images or any of the websites. You'll find out what this high energy ball milling is, what is the size of it, how do they do, what are the advantages, what are the kind of balls that they use there, so that with that energy they break the particles, and how much time they need to do this particular one, so that they get the nanoparticles. What are the advantages and the disadvantage of this component. On the other hand, we have this bottom-up approach. In this bottom-up approach, we are assembling the atoms. Maybe we are first taking from their ions, or if they are in atomic level, we are slowly assembling them to build up into their molecules from atom to atom, molecule to molecule, from cluster to cluster. We are actually building up the entire growth of a crystal using this bottom-up approach, and then we see that the molecules are assembled in a self-assembly fashion. They sit in their perfect place, and then we have a perfect crystal that is being formed there in the formation of this one. And in some of the cases, especially in physical approaches, we come across this one. We have a hybrid approach. In this hybrid approach, we have a combination of bottom-up and top-down approaches are combinedly used. If I'm using lithography, I'm using a bottom-up approach there. But at the same time, if I'm using lithography or laser abrasion methods, I'm using a combination of lithography and etching, so that I use both bottom-up and top-down approaches. Maybe in all hybrid approaches, they use both a combination of lithography and also both bottom-up and top-down approaches. This is how they use a combination so that they get their required design or required method of things that are required for it. Okay, then if you are really thinking that we need to prepare these nanoparticles, the biggest question is it true that only we are preparing, we are into it toward these natural particles? No, not at all. Even before we know something about these nanoparticles, our natural system has these nanoparticles, both in the wind, both in the solid, in the water, in all the biological systems. We have them inbuilt. The only thing is we could able to identify them very late. We could, some of the people have identified, but they never know that it is because of these nanoparticles. But these systems are there. These very extraordinarily smart particles are there in our nature. They are there. They have been formed during the volcanic activity. Continuously, they are approaching the surface of the earth through cosmic dust. They are being formed due to wind erosion. They are being formed due to bioprocesses that are happening in the water. Whenever we have streams coming down, whenever we have these natural waterfalls happening, whenever we have energy from thermal or solar sources, whenever we have our biomass being dissolved into our water bodies, whenever some sort of chemical reactions happening, in all these things, if you want to explain by taking various examples, I think this screen is enough to spend more than 1 hour to explain what are those areas where we have seen nature is preparing nanoparticles, where the size and how they are there, how much uniformity they are being formed there. In what are the areas? They are there in the earth. They are there in the water. They are there in the air. They are there in almost all biological systems, all the creatures, all the insects, all in everywhere. If you see the flowers, if you see the leaves, if you see many of the birds, if you see any of the creatures, you find that these nanoparticles are already there in the system, in nature. And if you try to look how they have been formed, we'll really wonder how wonderful nature is. So that's why now when we believe that these are already present, we are actually seeing how when nature is preparing by itself, how we can actually mimic the nature, how we can actually prepare these particles in an effective manner, so that we have a tailor-made according to our purpose. We have a required kind of material, so that we can use them for a specific purpose. So even in nature, we have carbon containing are there, we have inorganic are there. In carbon containing, we have a pyrogenic nanoparticles are there. We know we were using soot for a long time. Wherever there is a fire accident, we see lot of carbon, lot of soot is there in black fumes. We find that now carbon nanotubes are present in that, fullerenes are present in that, nano globules are present in that. On the other hand, for inorganic, they have been formed biogenically, they have been formed geogenically, and they have been formed in atmosphere also. And during this formation, we identified that in biogenic formation, many of the organisms like viruses, bacteria, they are also involved in preparing the nanoparticles. On the other hand, in the atmosphere, in the Earth's crust, we have these oxides that are being formed there, like magnetite, and these metals of silver and gold have been formed. Then we have iron oxides, we have aerosols from organic acids and sea salt. So this is a clear-cut picture of how these nanoparticles have been synthesized in nature. So if you now see this particular next slide, now you understand how nature is preparing them, so that we get a clue from the nature as we go ahead. If you see natural nanoparticles, we see that we find them in dust storms, both in terrestrial and extraterrestrial. These have been formed in forest fires. These have been formed in volcanoes. They have been found in ocean and water evaporation, and they have been formed in organisms. On the other hand, from the anthropogenic nanoparticles, we found them in diesel and engine. During the combustion, they have been formed there. In cigarette smoke, they are there. In building demolition, that fine particles are formed there. Then in cosmetics, they are present, and we are using them. In much of our indoor pollution inside our home, we have these very, very tiny nanoparticles there. And we are, by ourselves, we are engineering the required kind of nanoparticles for a specific use. And then we have other metals and other non-metals that we are finding out there in terms of beryllium, lead and copper, asbestos, cadmium, aluminium, nickel, chromium, manganese, iron, silicon. We have organic dust, coal and coal ash, and polymer fuels. See the sources from where we actually get these nanoparticles. Everywhere. If you go out, only thing is you don't have a device to immediately check whether it is in nano size, whether you have an instrument to immediately find out whether it is in nano size, but we find them there. So, and why we want to actually use it now is we have a lot of input, we have a lot of sources are there now where we can prepare them, at the same time where we can use them, so that the mankind's requisition can be fulfilled using these particular nanomaterial. Now, so in the maybe a couple of slides earlier, I told you that we have two approaches called as top-down approach and bottom-up approach, which once again I have shown the top part of the slide. Now in this slide, now I just want to mention you, if you are already a science, if you are a student or a faculty, if you are a researcher in this area, you will come across these particular words so frequently in your work. One is about if you are a physics student, certainly you might have heard about it. If you are a mechanical engineering student, you might have heard about it. If you are an electrical engineer, you might have, because all those people generally prefer to use physical methods only. They do, unless they are confident or they have a helping hand in chemical methods, generally they don't come and step into the area of physical methods. Like we have arc discharge method, electron beam lithography, ion implantation, inert gas condensation, mechanical grinding, ball milling, spray pyrolysis, vapor phase synthesis. If you see these physical methods, this left side part, except ball milling or except mechanical grinding, remaining all the methods are very, very costly. I don't say that ball milling is cheap, or I don't say mechanical grinding is cheap. Even ball milling costs somewhere in few lakhs of rupees. Because I don't think ordinary labs or ordinary colleges cannot go into that kind of equipment where they can acquire one and then convert their material from bulk to nano size, or initially bulk to macro size, and then from macro to micro, and then from micro to nano. These particular methods require highly sophisticated instruments to prepare them. On the other hand, you have chemical methods, and many of these chemical methods are comparatively very easy. Maybe I started with chemical methods and then I started checking the advantage of biological methods over a period of maybe 10 to 12 years. For the last 12 years, we are using these particular methods. That's why I could confidently stand this morning before you to tell that, okay, these methods are exclusively useful. You can use them at any point of time. They are almost all like fission chemistry. I don't think you require a highly sophisticated instrument. Now we have at least something like furnace, high temperature furnaces we are using maybe, but still many of these devices or methods that you need to use, like co-precipitation method. It is an ordinary chemical reaction. A chemical reduction of metal salt, simply use a reductant like sodium borohydrate or any of the ordinary chemical reductants in the lab, so that immediately you will get it reduced from a metal ion to metal. Then you have an electrochemical method or electrolysis. Then you have a microemulsion method where you use a surfactant in order to form. You have a pyrolysis method. You have a phytochemical method there. You have ultrasonication for sonochemical. We have a sol gel method with low temperature, less than 60-70 degrees. You can start doing this. You have a solvothermal synthesis. You have an excellent combination of chemical methods that are there. And the third one are using plants and then extracts, using microorganisms like bacteria, fungi, and actinomycetes, using algae, using enzymes and biomolecules, using industrial and agricultural waste. See this, the third combination. On one side, we have highly technical methods, costly in nature. On the other hand, you have maybe some simple laboratory chemical methods. And when you come to one more level on the biological method, I think you can do it by yourself. Even if you don't go to a lab, still you can prepare. For preparation, only for characterization you need to go for in this particular method. Okay, so in this physical method, I just want to, if somebody is first time trying to listen to this, so they should know. That's why I just kept a couple of things for your general understanding. So we have something called as mechanical milling, and so that you can break them up. Otherwise, you take the substance and then heat it to a high temperature so that it becomes vapor, and then start depositing it, and you have particles being formed at the nano level. So that's why these can be, see the kind of metals, kind of nanoparticles that we can prepare them, we can use them using high energy ball milling, like iron, cobalt, and alloys like iron, cobalt, cerium, cobalt, neodymium, and then we have single crystal nanoparticles. Then we have metal oxides like zinc oxide, ferrite, cobalt ferrites, and other carbonates, and we have carbon nanoparticles like graphite and pure carbon. We can actually have them by using this high energy ball milling. Then on the other hand, with inert gas condensation, we can use we can prepare metal nanoparticles like copper, silver, gold, platinum, and alloys or intermetallic nanoparticles or core shell nanoparticles. These can be prepared using this inert gas condensation. Then we have the other methods like sputtering, electron beam evaporation, laser ablation, and pulse laser deposition. We have a vacuum arc. See these technologies that are available. Excellent work on the other hand is going on with these highly gadgeted instruments, and then people are preparing these components. So all these 1, 2, 3. See this. These techniques will help you to prepare nanomaterial by using physical methods. And if you come to chemical methods, I just want to show you that, okay, we have a sol gel method, we have a chemical vapor deposition, colloid method, then we have spray pyrolysis. Maybe a wonderful series of these particular nanoparticles we have done over the last couple of years, decade and so. So we have prepared, we used sol gel synthesis in the preparation, we have used microemulsion using precursors, different kinds of precursors. We have these particular methods in preparing these particular components. Then we have nice hydrothermal synthesis methods where we can prepare both metal nanoparticles and metal oxide nanoparticles, metal sulfide nanoparticles. Then we have polyol synthesis where you can still use the similar kind. Then we have a chemical vapor synthesis, and then plasma enhanced chemical vapor deposition. And if you now see the kind of chemical approaches that you are seeing there, because from this component onwards we'll get a clue regarding how biosynthesis is going to helpful for us. In the sense, if you are using a chemical method, well, by the time you turn to a biosynthesis, you should understand what is that chemistry that is responsible for converting a metal ion into a metal nanoparticle, or what is that that is present in the biomolecule or the bioextract, which is responsible either for reduction or for oxidation. So we have chemical methods where you take trisodium citrate and then you can reduce metal ions into metal nanoparticles. Sodium borohydrate is one of the strongest reducing agents that we are using. We can use ultraviolet irradiation, gamma irradiation, laser irradiation. We have microwave assisted synthesis where simple reaction under microwave irradiation. We have sonochemical component is there. We have sono-electrochemical methods are there. We have simple electrochemical method. We can use polysaccharides like glucose. Simply add glucose or any starch to any metal ion. We find that it is being converted into metal ion. We have something like tolerance reagent, which many of the students at the degree level, whenever they do silver mirror test, ammonical silver nitrate, they simply add tolerance reagent, and then they do it. They do the tolerance test. They do the failings test. In both these particular components, even though they do a test and then they see a silver mirror or a copper oxide red precipitate in failing test, the only thing they stop there at that point of how that has been formed. But what actually they have done in that test is they have prepared copper oxide nanoparticles in failings test or in tolerance test. They prepared silver nanoparticles, and those silver nanoparticles deposited inside the test tube, and then they look like a silver mirror from outside. See, an ordinary reaction which was just a confirmation test at one particular point is basically a method of preparation of silver nanoparticles inside a test tube. That's how we find this, so that these methods will be helpful for us in understanding that. Okay. So we have a couple of reagents there that we use, maybe sodium citrate or ascorbate, sodium borohydrate. We can use elemental hydrogen for reduction, polyols. We can use then the tolerance reagent for silver ions. So this is a simple figure showing silver nanoparticles formation. If you take silver nitrate solution, it is basically a colorless solution, but once it is reduced, it can be of any of these particular colors, maybe pale yellow to maybe little orange or even little brown in its tinge. If you find any of these colors being formed there, in the for the silver nitrate solution, it's an indication that silver nanoparticles have been formed there. So from a clear colorless solution to a shift of the color by a reduction process where a color changes, it is an indication that because it is impossible to identify the silver nanoparticles being formed there in the solution with our naked eye. It is not possible. But our naked eye can identify the color of the solution. That color indicates that nanoparticles have been obtained, nanoparticles have been formed. Even the color intensity gives us an idea regarding the average particle size as you go through, or the other components in which this particular indication will be giving us an idea into it. Okay, so we have an excellent method of converting or preparing metal nanoparticles or metal oxide nanoparticles, or even a combination of what we call it as maybe alloys, maybe core shell nanoparticles, or any of those particular things. But as we slowly move from chemical methods to biological methods, we have excellent things. You may ask how many things are there. If you can have 100 plants, 100 different plants with 100 different kinds of leaves, you can prepare silver nanoparticles with almost all 100 different leaf extracts. That's what this particular method of preparation of nanoparticles with in biological methods. That's why you can see excellent or new works being reported almost all every day in almost the best journals, because they are identifying the new plants, new plant parts, maybe flowers, maybe leaf extract, maybe root extract, maybe the fruit extract, or any of the parts. Then they are trying to prepare nanoparticles in different components, and they are now in a position to control them. They are trying to identify what are the things that they can use in order to prepare them. Okay, so we have a particular things that are available now. You can prepare silver, gold, mercury, copper, platinum, palladium, titanium dioxide, silica, zirconium dioxide, cadmium sulfide, lead sulfide. See the kind of particles. You can prepare them using microorganisms. So you need to be a person who has a knowledge about microorganisms or bacteria or fungi. If you have a source so that you can take this particular component, you can use that source in order to prepare a similar kind of synthesis in order to prepare. So we have a biotemplated assisted biogenesis of metal nanoparticles, especially silver, gold, and platinum. They have been used. Palladium, people are preparing, so that they are extensively used now, especially as antimicrobial, antibacterial, antifungal. In so many different ways, they are using this particular component. I just want to give you one example. I just want to show you one example how you can prepare it. If somebody have a habit of using, I just want to just go to this slide first and then come back. I know many of you will be nowadays consuming green tea. If you have green tea with you, I think you are one step away from preparing your nanoparticles using biosynthetic method of preparing nanoparticles. That's how close you are. If any time when you have a green tea, if you just take that green tea, take the extract, that's how we are actually drinking green tea. Take some hot water and we are dipping the pouch, and then you are simply using dip, and then you have extract, and then if you want, you are adding either you are drinking it as a lemon tea, or you are drinking with honey or any of the component. If you stop there without drinking and then have that green tea in your cup, and then your reaction medium is ready. That much simple is that now. With that green tea, imagine you can prepare any metal nanoparticle, any metal. If you have a metal salt and if you have a mechanism to monitor how the reaction is going on, maybe this one cup, this one solution can teach you how to prepare your metal nanoparticles, how to prepare by biometric method, biosynthetic methods, and this is how it looks like. Simply take silver nitrate solution. You have a green tea leaf extract in beaker B, mix both of them, and after some time you find that the nanoparticles of silver are being formed there in the solution. As simple as that. It depends upon maybe little temperature, but not hardly more than few minutes. I think within less than 5 minutes, you find forming these particular particles forming inside your teacup or inside your beaker. If you are trying to do it in a beaker, maybe there. This is where we now looking into this. If one plant extract can give this kind of preparation of biosynthesis of metal nanoparticles, imagine how many plants we have around us. every leaf, if you see around you, if you can collect that leaf, make a leaf extract like your green tea extract, and simply bring it down, and you want to check how much time, what is the size of the particle, what is the shape of the particle. Maybe enormous research is in your hand to initially be a master in this area, be a master, because it's not that once you get this particular third beaker, you have a brown colored or some other colored solution in your beaker, and then after that what you have to do is another big question. It won't happen as you wish, but preparing that particle is in your hand. If you take the same lemon tea, add little copper sulfate solution into that, copper sulfate solution is blue color. The moment you add it in blue color, within few seconds, you can slowly see that it is turning into orange color or brown color. You can see the formation of copper nanoparticles being formed there. That much simple. You can prepare almost all including iron. Simply add little ferrous sulfate into this green tea leaf extract. You can identify that it is immediately converted into zero valent iron or iron nanoparticles being formed there. So this is where we are looking into this particular component. So we are using biomolecules, we are using the components present in our biological systems. What do we have in these biosystems? These plants have enzymes, these plants have proteins, these plants have amino acids, these plants have polysaccharides, these plants have vitamins in them. So the components that are present, they are responsible now for the reduction or maybe for the oxidation of the material that you are taking in order to convert them into nanoparticles. Maybe how they really stop in the preparation of nanoparticles, why they don't go one more step so that there is a agglomeration of this particle. Maybe we'll be seeing very soon. So if we want to see the same thing happening with bacteria is also having a similar capacity to convert silver ions into silver nanoparticles, like E. coli, then Subtilis, all these bacteria, Bacillus, they all have the capacity to convert the silver ions into silver nanoparticles. Then we have fungi have this. Different fungi have different capacity to prepare silver nanoparticles, to prepare gold nanoparticles. So people started checking various kinds of these biological systems for the preparation of different kinds of nanoparticles. Now, why suddenly we are looking into another dimension of this particular one? One is they are green in nature. We are not using any strong chemicals. We are not using any of the components. It's a very green method, highly eco-friendly, low cost. We can use it at the laboratory level, at the individual level, or we can still use it for larger scale synthesis. One of the industry in Visakha is now preparing silver nanoparticles using one of the plant extract. And they have identified very fast reduction of silver nanoparticles. Now they are using it as an antibacterial solution, for as mouthwash or other component. Now they are going into the commercial component as a mouthwash or as in the toothpaste, in all other components, or for other body lotions. They are using it, and even now they are testing your many of the, after COVID, they want to know how our masks, which we are using it, if they have these silver nanoparticles covered, how much it is reducing how it is effective in terms of various kinds of bacteria or any of the microorganisms. So that's how they are actually checking them. So it all depends upon how we prepare it, and they have different components that are present in green tea or black tea leaf. There are different polyphenols that are present there, flavonoids and other all that chemicals that are present in various leaf extracts. They are everything is now being tested in order to identify how these biomolecules are preparing are actually doing the chemical reaction in this particular context. So I just want to show you the actual process or how it is being done there in this context regarding how green tea is being used for silver nanoparticles or gold nanoparticles. Even though we have done with different plants, we are looking for new leaves, new plant parts, new plant extracts, maybe from their root extracts or leaf extract or their bark extract. We want to see their composition and how they have an effect of it. Many of the people in pharmacy and chemistry, earlier they worked on natural products and their extraction and their microbial activity or a biological activity. Now we have gone one more step, not only their innate biological activity, but how these particular extracts can be used for the synthesis of various nanoparticles, and what could be the synergic effect. If every extract has an impact on either bacteria or microorganisms, if that can also combine with other nanoparticles, which it has a ability to convert, then what could be the synergic effect? Because silver nanoparticles and gold nanoparticles have extensively studied for their antibacterial, antimicrobial, antifungal activity. But once they are combined with these bio-mediated methods, bio-mediated synthesis, how could they actually show an effect on it? Okay. In this particular context, the different kinds of leaves have been taken. If you want to know how they do it, maybe this is what that particular this slide tells you. You take any leaf that you find it. Then you just finely cut the leaves into small pieces, then add water, then boil it so that you have a leaf extract. Then take the metal precursor solution, add it to leaf extract, then slowly stir it, or if little, sometimes some sort of heating also required. Then bioreduction takes place, and then once these particular nanoparticles are formed, then separate them using any of the methods that are available to you, and then you can identify them. You can study their properties by various characterization techniques. Maybe you need to know how these nanoparticles need to be characterized. Maybe it's altogether a different dimension to explain how nanoparticles are identified, what are the techniques that are available now, how do we identify the surface, how do we know that the things that are identified in this image, maybe a TEM image that you identify, that how does it tell us that what is there in that context? Maybe another dimension of study, if somebody is trying to really work in the area of nanotechnology, before you do this particular exercise, maybe if you really just want to know that these things are possible, I think you can take any green tea leaf extract or any leaf. You have thousands of leaves around you. Simply pluck some 10 kinds of leaves and then make a leaf extract into 10 different cups or 10 different beakers. Add the same salt into it, same salt solution or a precursor solution. you will be knowing which one does it fast, which one is taking more time, which one is the slowest, which one in what combination you can identify. If you follow a similar pattern, you'll identify even the time factor also or other conditions that it will be knowing. But when you want to see this particular context, what actually we are trying to do is we want to, for all metal nanoparticles, these metals are available with us in their salt form. Like silver, we have it in silver nitrate form and it is in Ag plus stage. Now we need to reduce it so that it becomes Ag0. That's how we are trying to do it. Similarly, if you want to gold, you take a gold salt and then do the reduction reaction so that you have gold nanoparticle. If you have a platinum chloride salt with you, do the reduction reaction, you have a platinum nanoparticles or palladium nanoparticle. If you have a nickel salt, you can convert into a nickel nanoparticle. If you have a copper salt, you have convert them into a copper nanoparticle. So depending upon what actually you want, you need to take that corresponding salt and then you need to know what is that reaction that you have to do. If I want to make ZnO nanoparticles, I need to do oxidation. I have to convert it from zinc salt or zinc ion to zinc oxide, and I need to have a different mechanism. It's not a what is that I have to do so that I get zinc oxide nanoparticles or copper oxide nanoparticles or ferrite nanoparticles. If I want to have those components, I need to first of all understand the kind of reaction I require, and that helps me to identify the kind of reaction that I require to do it. Okay, then once I have it, I should know what is that reaction to take place. The second thing I should know is it should not be agglomerated, or it should be in its nano size only. For that, I just want to show you this. Okay, this is what happens in many of the formation of nanoparticles. If you take silver salt, it will contain silver ions there. If you use a chemical reducing agent like sodium borohydrate, it immediately, in fraction of a second, silver nanoparticles will form with Ag0, as that nuclei will form, and slowly they will be forming into silver clusters. If you do not control them, initially they form silver nanoparticles. If you do not have a mechanism to stop them at that component level, they will once again join together and you have a larger agglomerated size. They will not be in nano size, but they'll grow, they will be joined together and you find in macro size. But if you are using a precursor there, slowly this precursor will help in identifying these nanoparticles. It will control the growth and it will be stabilized. In the sense, every silver particle will be surrounded by some stabilizer or by some precursor, so that the required size of the nanoparticle will be maintained in this particular context. So for all the biological systems, we have a natural precursors that are present there. One is they have certain reducing agents, maybe like polyols, maybe like polysaccharides, maybe some aldehyde groups which will be reducing it. At the same time, the other moieties inside the leaf extract, they use as the stabilizing agent. They are used as stabilizing agent, so that they will not allow for the sedimentation, or they do not allow for the agglomeration process. So we require these particular one. One is we need to have the required chemicals. The second one is we require certain surfactants or like thiols, amines, acids for interaction with particles, and also for their stabilization, so that they do not sediment or agglomerate. Similarly, we require certain stabilizers which will be used as which include some surfactants or polymers which are used as their reaction vessels. And similarly, we can use polymeric compounds such as polyvinyl alcohol or polyvinyl PVA, PVP kind of things, so that they will be used as protective agents to stabilize these nanoparticles. So that's why when we are preparing these molecules, when you want to know how what kind of what size of particles you want, the second level of reaction that you are taking care is not only the natural biological extract or a plant extract or a fungi or bacterial extract. At the same time, you need to have these stabilizers to stop agglomeration of the formed nanoparticles. Maybe this is another small excellent work. Many of you have this aloe vera in your backyards or somewhere. Take little aloe vera gel into your hand and make it a solution and use silver ion there. You'll find excellent formation of silver nanoparticles using this, and it is so clear also. It is because aloe vera gel is a clear solution. The formation you can see very clearly because there is an excellent color change that is forming there. So we have. That's why this biosynthesis is giving us a new dimension into the formation of metal nanoparticles, oxide nanoparticles, the sulfides and other kinds of nanoparticles. And as we go into it, we need to understand how this is being done there. So for that, what basic information that we require is what is made up of. If you know about a guava leaf, you need to know what are the chemicals present in it. If I am talking about green leaf, the first thing that you should know is what are the chemicals that are present in green leaf, which we every day take into our body. If this green leaf can convert a metal ion into its metal nanoparticle, now the question is, when you are drinking, it has the same capacity to convert metal ions into metal nanoparticles. Maybe a similar reaction may take place inside your natural organism, inside your digestion tract, inside your stomach. So it has a capacity there. If it can prepare, then what is the impact of those components that are being produced there? So there is a wonderful things that we need to learn, not only from the context of how these things are being formulated there. Then you have before I come, we have other examples. I just want to show you a couple of examples before I go there. We have iron oxide nanoparticles being prepared from seaweed. If I just go to Visakhapatnam beach and then take go to any rock there on the seaside, I can see some seaweeds there. Simply take a small sharp object and then scratch them, the dried ones or brown seaweeds. I can bring them, I can use them as a medium, a biomedium, where I can use them for the reduction of ferric chloride into ferrite nanoparticles. Then I have, because they have these particular chemicals or these biological constituents in them, which convert metal salts into metal oxides, or zinc sulfate or zinc chloride into zinc oxide nanoparticles. So we have an unbelievable amount of natural products available around us. We have microorganisms that are present to prepare. We have for metal articles, then we have bacterial components, we have bacteria to convert alloys, we have fungi to convert nanoparticles. Actually, I just want to show you some of these examples also, but I know my time constraint is roughly around 45 minutes to 1 hour. So I just confined myself. So in this particular context, if you have a desire, if you have a need, if you feel that you want to do some work in this area, maybe there is no limit of identifying new plants, new organisms, new bacteria. All these things are available for you. You should know what is the purpose for which you are doing, what is the mechanism of if something is doing, what is that chemical that is inside which ultimately doing this particular conversion process that helps us to step into this particular area boldly and confidently. So I stop. I think I have given you a broader picture of bringing you from an understanding of what these nanomaterials are and from how to prepare from a technological context to a teacup. So you're preparing a nanoparticle is now in your hands, in your teacup. If you have one Taj Mahal tea or any other tea bag in your hand, maybe that tea bag with little hot water is your reaction mixture, is your reaction medium. That can help you really test whether nanoparticles can be formed or not from any of the sources or any of the methods that literature talks about. So I thank the organizers for giving me this opportunity, and I really thank. If you have any questions, I don't mind asking, but I think the organizers will be telling the modus operandi from this time onwards. I thank you so much.
So thank you, sir. Thank you so much, sir. Thank you, sir. Dear participants, if you have any doubts, please post your doubts in the YouTube chat box. Then sir will clear your doubts. If you have any doubts, please post in the YouTube chat box. Ramakrishna sir?
Yes, sir.
Otherwise, you can send me the questions later on. I can respond to them. No problem.
Okay, sir. Thank you, sir.
Yeah. Any questions? You collect them.
Sir, any questions there, sir? Any questions?
Yeah. You collect the questions and forward to me so that I can send your answers. You can send them back. No problem.
Okay, sir. Okay, sir. Sir, is there any questions, Ramakrishna sir?
Sir, I'm
So, okay. Sir, can I conclude?
Yeah. They agglomerate and then they convert it into silver mirror. They are formed and then only they are agglomerated onto the surface and it looks for us like a silver mirror. That's how it is formed.
Sir, another question.
They can form from lower temperatures to higher temperatures. Suppose if you are trying to do with some bacteria, you cannot boil them at 100 degrees because by that time bacteria will die. So you cannot prepare nanoparticles with bacteria at high temperatures or any of the fungi at high temperatures. So many of the things they'll be at room temperature or even at cooler temperatures. But some chemical methods, they require higher temperatures for the final formation. Some of the chemical methods we heat up to 1100 degrees, 1200 degrees for the final formation into their crystalline structure. Okay, that's how it forms. But in all the biological forms, we don't heat them more than maybe little boiling. I think other than that, we don't go for all plant extracts, boiling is more than enough. That like temperature of 70-80 degrees, it will be sufficient to convert them into the required kind. You use any salt, you use any leaf, it will form. Yeah, one of the finest, simplest nanoparticle you can form is take copper sulfate salt solution, but you need to know the concentration. It's available in the literature. Simply prepare that concentration and then use any of the leaf extract. Any leaf which is available outside your house, guava, mango leaf, or any leaf. Yeah, ordinary, commonly available leaf extract you prepare, you add copper sulfate. Within seconds, you start seeing the blue color turning into that red color, and you know that it is being formed there.
Sir, one more question, sir. Sir, how we can use plants to make nanoparticles, but are these used in most of the labs, or do they still use expensive methods?
No, now it all depends upon the purpose. If I want for a specific purpose and I don't want any other impurity, then they will be doing a simple chemical reduction. So they use sodium borohydrate and they reduce it. So they can remove the sodium borohydrate by washing, and they can centrifuge these copper nanoparticles. So multiple washings and then by centrifugation will separate these molecules. If I'm using, if I want for a specific purpose, both as a microbial, for antibacterial study, or an effective study for a cancer treatment, if already the plant is used for cancer treatment, how these silver particles club to that previously one can enhance its effectiveness, right? So it all depends upon for why you want that. Why it's not simply adding something, but you need to know the very purpose of preparing and very purpose of using it, where you want to use.
Sir, one more question, sir. Sir, which method is best for preparing plant-based nanoparticles?
Now there are thousands of plants, thousands of methods are useful. If in my opinion, plants are easier for me than using bacteria or fungi or microorganisms, because I do not have, as a chemist, the technique to handle bacteria or microorganisms or virus. I don't have that. So that's why unless I know how to get the bacteria and preserve it, then only I can make a solution and then convert it. If it is a plant, I don't require expertise. I can simply take any leaf. I go out of my lab. There are so many new leaves are there which I don't know, but still I can check them. How that leaf is helping me to prepare my nanoparticle. But if you ask me fungi, I do not know where. First of all, I should be an expert in the area of biochemistry or biotechnology. I need a help from that branch to identify what is that fungi or bacteria and how I can prepare a solution for it. Then only I can use. So as a normal researcher, using microorganisms is a difficult job for me than using plant leaves. Okay, that's how I look to it. So whenever I want bacteria, I have to take help from somebody from biotechnology or microbiology department. They will be helping me out in this particular endeavor.
Sir, please give me the reason. Why does silver nanoparticles produced by plants are more stable than those produced by other organisms?
There is nothing like plants is more stable than, there is nothing like that. Plants have other components inside their extracts which naturally act as stabilizers. There is no need for you to act another stabilizer. For if it is a bacteriological, you need to add a stabilizer so that they will not be agglomerated there. So plants have a lot of in tea extract you have so many other chemicals. These actually are encircling the nanoparticles, and they do not allow them and they make them stable. That's how it happens.
Sir, what is the reaction mechanism observed between the leaf and silver salt?
Leaf, leaf doesn't directly, never leaf will directly react with any of the thumb. One of the chemical component of a leaf will be reducing metal ion into metal nanoparticles. That's why I said I have shown you what are those components you should know. Then if you have a glucose molecule in your leaf, that glucose molecule or that aldehyde moiety or a alcoholic moiety or a phenolic moiety will be responsible for reducing it into a metal ion to metal nanoparticle.
Sir, can you share your mail ID so that we could clarify our doubts during the synthesis?
Yeah, take it from the organizers. I think they'll be helping you out.
Okay, thank you, sir. I will give, sir. And want to know the level of achievements made by Indian scientists or chemists in the nanochemistry.
Just go Google it. You have so many extraordinary scientists working in this. Actually, I learned this from one scientist by name Dr. Rajendra S. Verma. Now he's in US and he's from India. He actually really inspired me, encouraged me for using different green methods. He works in US Environmental Agency. One of the topmost scientists from India working in US in this kind of green area. Now he's into so many kinds, including ultrasonic, including microwave assisted synthesis. That's why after learning so many things from him, we called our research group as. So there are so many scientists in India, in all IITs, all IICT, NCL Pune. They are all thousands of scientists working in India in this particular area. Just simply Google different works, you'll find them. And number of research works are available for you to understand this kind of work.
So that's it, sir. That's it, sir.
Thanks so much. Thanks so much.
Thank you, sir. And sir, yes, thank you, sir. Actually, it is most useful session to all the participants, sir. Thank you so much, sir. And I want to conclude this session, sir. I must thank to today's speaker, Dr. S. Paul Douglas Garu, to accepting our invitation again. Sir, we are very fortunate to have you in this FDP, sir. Actually, we are all gain so much of knowledge in this session, sir, regarding nanoparticles. Thank you so much, sir. And thank you to all the participants over here to register our FDP. Thank you very much. Thank you, sir.
Well, thank you so much, all the organizers, especially Principal Garu and Director Garu, for giving me this opportunity. Have a wonderful day. And all the remaining 3 days also, I'll try to join so that I also gain a wonderful experience from all of you. Thank you so much.
Thank you, sir. Thank you so much.